synchronous versus non. So, I am just ignoring the losses here. So, this is your synchronous, because both the switches are driven by the clock in this case, and this is synchronous and bi-directional. So, it can sink the current and source the current both, because this bottom switch can conduct and it can draw the current from the output. This could be another way to implement your buck converter, and this is non-synchronous because the bottom switch is only this top switch is controlled by PWM, and bottom you do not have any switch. So, your diode will conduct on its own. So, in this case current can flow in this direction and in this direction. So, when you are looking at this direction, the current is basically okay. Anyway, okay. So, current can go from V out to ground and VDD, or as well as VDD and ground to V out. In this case, current will only flow in one direction. So, if this is your load, so load can go like this, or this here load can always go like this. Okay, so this is your there is the advantage of having a bidirectional. So, we will talk about that later. So, in terms of efficiency, which is better, synchronous or non-synchronous? Go back to your losses. How do you calculate the losses? So, for diode there is no R, you have to take the diode drop. So, let us say this is a normal diode, what will be the forward voltage? 0.7. So, 1 amp and 0.7, 0.7 watt you loss in multiplied by your 1 minus D. So, let us say even if you have a 50% duty cycle, okay, 350 milliwatt is lost in the diode itself, and in the other case we were looking at total loss of only 50 milliwatt in the switches and 50 milliwatt was in the inductor. So, your non-synchronous will be lossy, and that is why we do not use normal diode, but we use Schottky, because Schottky has a lesser forward voltage. So, even if you use a Schottky, it will be 200 to 300 millivolt, roughly. So, still in terms of efficiency, your synchronous will perform better than non-synchronous. So, if your load current in case of non-synchronous, when the inductor current goes negative, this will not conduct. Negative means from output to, so reverse, if your reverse current diode, we cannot allow reverse current, it will just block it, because it will get reverse biased, and that is the reason it is only unidirectional, not the bidirectional. But here switch is a bidirectional, current can flow from any direction, source to drain or drain to source, if you are using MOSFET, and that is why this one is synchronous, one is bidirectional. So, both have its own advantages and disadvantages, we will talk about later. In terms of efficiency, at high load the synchronous is better, but at light load your non-synchronous may perform better compared to your synchronous, and that is why we forcefully operate this synchronous in a non-synchronous mode at light load, and will, so basically you convert this switch into a diode by using some kind of a logic, and so we will look at those circuits later when we talk about your discontinuous conduction mode and all those. Okay. So, let us look at the control techniques. So, it is a PWM control that we already know, and usually we define it as voltage mode control, current mode control. So, what you have is your L, C, so usually that is how you implement your switches. You can use bipolar also, but since we use MOSFET technology, so we just use MOS. So, for high side you use PMOS, for low side you use NMOS, and these MOSFETs are quite big. So, you usually use gate drivers which has non-overlapping clock, so gate driver is nothing but its buffer, and you feed PWM here. So, it generates two clocks with a non-overlap, basically they are non-overlap in the same polarity, because one is PMOS and NMOS. So, when this is high, this should also be high to turn it off. When this is low, PMOS gate will also be low, so it will turn on PMOS, but there will be no. So, non-overlap is basically also called break before make, which means before you turn on the other switch, you first turn off the current switch and only then you turn on the next switch. And this comes from PWM comparator, minus, plus, and this gets a sawtooth waveform, some control voltage, compensator, Vref. So let's say I have a feedback resistor, just like we had in case of LDO. This is your VFB. Okay. So this is your voltage mode control. If this is going 0 to, let's say, Vm. So what happens? You take the feedback, compare it with the Vref. So it will generate your error signal V, and that error goes into the compensator. So compensator, you can assume it has amplifier and some R and C, just like you have in case of LDO. So it's a error amplifier. So, and this error will get converted into a control voltage, and this control voltage will settle to get the desired duty cycle here at PWM. So now let's see how your duty cycle is getting generated here. So now this is your sawtooth going 0 to Vm. If this is my control voltage, so how will your PWM look like? So VCTRL, let's say greater than 0, and this is going 0 to Vm. So whenever you reset to 0, what will happen to the PWM? When this, let's say I call it VRAM. So this is your, so when VRAM is 0, V control is more than 0, so PWM will be high. Okay. And at this point, what is happening? Your negative terminal of this comparator, this is nothing but comparator, is getting higher than V control. So this will go to 0, and it will remain 0 until again gets reset. Okay. Then again will go high. This should be high. Huh? Okay. This is your PWM. So in terms of V control and Vm, if I want to write the duty cycle, what will be the duty cycle? So if let's say V control becomes 0, what is the duty cycle? 0. Okay. If V control becomes Vm, what is the duty cycle? 100%. So it's just a linear function of your V control. So D is nothing but VCTRL over Vm. Correct. So that linear function will have this slope, and the slope is nothing but your gain. So in terms of duty cycle, it's this. So when you model your PWM, that's how you define the actually. So the gain will be 1 over Vm for that. So we'll try when we model the small signal, then we'll see. We have to model each and every stage. We model the power stage and this PWM modulator or PWM generator. So this is called PWM modulator. So, which means your duty cycle is controlled by the voltage here, which is control voltage, which is VCTRL. So, let us see what happens in the current mode. So, in the current mode control, this is my IL, this is PWM. So, what you do actually, you set your duty cycle at some clock, reset clock. So, when PWM is high, inductor current will rise, and when it reaches certain peak, let us say I peak, you reset the duty cycle. So, you are looking at the inductor current information rather than the voltage information. So, here we are not looking at the inductor current at all, okay. But in this case current mode, you look at the current. So, obviously the compensator will be here, and since so what you do actually, you take the current from here and add up in the control voltage, okay. So, and then so there is no ramp as such here. So here you are comparing sawtooth with the control voltage, and control voltage is DC. Here what you do, you keep resetting the duty cycle or setting the duty cycle. So, it will go to 1 as soon as you set, and when the current reaches the peak, some peak, you reset it. So, there is no sawtooth in case of current, because that ramp is basically current coming from the current itself, because the inductor current is a shape of ramp, okay. So, you do not require any sawtooth here. So, no external VRAM is used, okay. So, theoretically you do not use, but in practically when you implement, there is a small ramp you use for compensation purpose. So, when we look into this current mode in more detail, then we will talk about that, okay. So, what we will do when we analyze this small signal and everything, we will do everything for voltage mode control, and we will talk about the current mode a little bit more detail later, because for understanding purpose, voltage mode is better compared to your current mode, because the compensation and everything is a little bit complex for this, because you use type 1, type 2, type 3. There are 3 different types of compensator we use here, but in case of this current mode, you do not use type 3, you use only type 2. Type 2 means you use only 1 0. In this case, you require 2 zeros, because you have 3 poles in the system, 2 poles coming from LC, another pole comes from your integrator, which is in the feedback amplifier, okay. So, we will look into more detail about the compensation, everything, considering the voltage mode control. Another reason is voltage mode control is widely used compared to your current mode, because current mode has certain limitations, some noise performance is not better, and operating this at a very low current and very wider duty cycle range is not easy for current mode, but voltage mode can easily be used for wide range of load current and duty cycles, and that is why we prefer voltage mode or current mode over current mode for wider range of duty cycle operation and wider range of load current. So, we will look into voltage mode in little bit more detail compared to this current mode. So, compensation everything will do in detail for this particular voltage mode control.